Okay, thank you for joining. My pleasure. I'm Laurent from NETGEAR. I'm the Director of Product Management for the Managed Switches. NETGEAR is a founding member of this great SDVoE Alliance. And during maybe 15, 20 minutes max, I want to explain how properly interconnect switches, okay, in order to build an AV over IP system. Of course, we can build a AV over IP system on a single switch, but sometimes it doesn't scale enough. Sometimes you may need 1, 2, 3, 4, 5, 10, 20 other switches. And in order to interconnect switches, you can actually use 3 different methods. And I'm going to go through each of these methods. We are going to configure the switches with these methods. And as a conclusion, we will just try to make our mind, okay? Look at the pros and the cons, benefits and drawbacks for each of single methods. The 3 methods are stacking. Stacking is the first method of choice when it comes to connecting several switches together. Second is the good old link aggregation, or lag, or trunk, or ether channel. And the third one is going to be quite new, and I hope you're not going to be too much afraid of it, but you're going to see that there is other cool ways of interconnecting switches together using VLANs. So again, sometimes a single switch is good, okay? If you can pack all your AV over IP devices on a single switch, it's better, because at least it's a single fabric. But as soon as you have a larger installation, you will have to make a decision how to interconnect your switches. Let's go with the first method. The first method is called stacking. So I don't know if I have network engineers in front of me right now, but stacking is a very ancient, good method when it comes to aggregating several switches together. Stacking means that we need to have stackable switches, of course, and with stacking we are going to aggregate several switches in one logical system, okay? So it means that we are going to use stacking ports, and we are going to use one switch as the commander, the stack master, the management unit. And this master switch will handle the data plane, the control plane, the management plane, and all the other switches in the stack will be considered as members of the big switch, okay? So you can think of a chassis, maybe, with a hypervisor or supervisor module. The other switches are just member of that large, unique logical switch. So that's a good thing, because instead of manipulating several switches, you can actually manage only one, and the whole stack is going to behave as a single switch from the inside or the outside of the network. So let's take an example together, okay? It comes to a 72 by 72 typical installation for video over IP using SDVoE technology. So I have 72 sources, 72 transmitters, T-axis, and I have 72 other receivers, R-axis, connected to the displays, okay? And my way for that example is going to be, I am going to have 24 of these transmitters and 24 of those receivers on every single switch, maybe on a dedicated floor, and I'll have another switch on another floor and the third switch on the third floor. And of course, I need to connect them into a single system. And in order to sustain 24 transmitters, saying for instance that they must run at 10 gig Ethernet, 24 times 10 means 240 gig of bandwidth. So that's probably the reason why we are going to use 6 of those 40 gig links. 6 times 4, 24, 240, that's the right count. I will be able to transport back and forth 24 streams of 10 gig each in between the switches in order to sustain this installation. So I have 3 switches, and my first way is going to use the stacking. We are going to stack those 3 switches using those 40 gig ports in stacking mode. So how are we going to do that? Well, we are going to connect, for instance, to the web interface of the first switch, let's say the switch on the bottom left, and we are going to use the system stacking menu in the web interface, and we are going to select those ports on the lower left and alter the configuration so that we transform those Ethernet ports into stacking ports, okay? And of course, when it's done, please save the configuration so that the switch can remember. If you don't like the web interface, you may want to use a command line using CLI. On the bottom left switch, we are going to enable the configuration, go to the configuration mode, assign priority and the stacking number for the switch, and we are going to we are going to connect and select the ports 7, 8, 9 and alter the configuration and change the configuration to the stacking mode. We are going to exit the configuration and save that configuration. Of course, we need to do that 3 times because we got 3 switches. When it's done, when the configuration has been changed, those ports are stacking ports, we need to reboot those switches and you're done. You have a working stack, and even if you have a power failure of any sort, each time the switches will reboot, they will always be a member of that stack. So that sounds good, right? It's a good method because it is a single switch at the end that you have put together. But as I said, you still need to be aware that the traffic, those 24 streams, need to be somehow passed through those stacking links. And that might be sometimes a challenge. That's why we want to explore other methods. So after stacking, you have the link aggregation. So the older guys like me in the room might remember that we used to call that trunking, 802.3 AD, Ether channel at Cisco and all that. Well, nowadays the norm for that denomination is link aggregation group, okay? So in this solution, you don't stack. Switches remain totally independent, okay? Totally independent switches, but still you want to aggregate several ports in order to allow for more bandwidth from one switch to the other. Let's take another example. This time we are going to build an even bigger over IP installation. I have 128 transmitters, video sources, and 128 receivers, let's say displays. And this time I'm going to have an even distribution of 32 TXs and 32 RXs on every switch. So let's do the math real quick so that you feel confident with the solution. If you are going to emit 32 streams at 10 gig each, you need 320 gig of bandwidth going left to right. If you use 8 ports of 40 gig Ethernet, 8 times 4, 32, times 10, 320, you have a line rate, non-blocking capability left to right. And of course, you have this link, yellow link in the middle, fully bidirectional, full duplex, so you can also receive 32 other streams, maybe, for your receivers. So this is what we want to achieve, and at the center of this network, we need a core switch, right? Ethernet is a star-based system, so you always have a core switch and then access switches. The core switch will interconnect all these ports so that you have a line rate installation. So let's create those link aggregation groups. How are you going to do it? Well, again, you may want to connect to the web UI on the switch. This time it's not a system layer 1 stacking thing. It's going to be a switching layer 2 lag link aggregation group. And we are going to select the yellow ports we want to use as an aggregation to put them together into a virtual link aggregation group. We are going to choose one parsing algorithm in order to do the hash in between the lag legs. And usually for multicast, the best one is the destination of the transmitter streams. The destination of the video is always the multicast group. So this is the best way probably for the algorithm. If you don't want to use the web UI because you are more familiar with the command line, you're going to log to the first switch, enable the configuration, give a name to the link aggregation group you want to do. This is the first. We are going to call it 8 ports. We are going to select that load balance mode based on the destination, the number 2. And then we are going to sequentially add the yellow ports, so the 171, the 175, and so on, to that link aggregation group. When it's done, we are going to exit, save, and reload the switch. So the link aggregation has been done on the first switch. Of course, I need to do that for all the switches, the second switch, the third switch, the fourth switch. And if you put together a link aggregation on one switch, you need to have the exact same at the other end. So the central switch will also just need to have those groups configured. And then you're up and running, and this time we have used 8 ports, link aggregation groups. Remember, I told you that, well, it's similar to stacking, but this time switches remain independent. We still have the same kind of potential issues when the flows, the streams are going to traverse from the left to the center. How can we make sure that those video streams use the proper link, not to saturate or oversubscribe one of these legs in the link aggregation? And that's a fundamental problem. And of course, we do our best, but sometimes some customers or myself would like to have more control on that. So that's why I want to introduce a third method today. We have reviewed stacking. It's good, easy, but maybe some difficulties sometimes. We have reviewed link aggregation, which is widely used in most IT networks. And now I would like to present a third method that will not use any kind of link aggregation, any kind of stacking. And this method is going to be based on VLANs. So bear with me, we are going to use a third example. And intentionally, I used a pretty large installation. As you can see, I have a whole lot of encoders and decoders on that, in that diagram. I want to have any encoders and decoders on many floors, on switches, and I have 40 of them, 40 encoders and decoders per switch, all connecting back to the core switch. And because I have 40 of them each time, I'm going to use 4 times 100 gig in order to have a line rate installation. And this time it can be whatever, encoders, decoders, mixed or not mixed, doesn't matter to us. So of course, if we had some kind of little issues in the parsing, that would be a big problem to manage. So let me show you how we are going to do it. One of the best ways of doing it is to cut the switch in small pieces using very simple port-based VLANs. So a VLAN is actually a segregated, smaller layer 2 domain, like if I had a different switch each time. The blue one will be the first 10 ports, okay? So my blue VLAN will connect those encoders and decoders. And these 10 ports will only talk to the blue uplink on the right, which will be part of the same blue VLAN. This way, I'm making sure that my 10 encoders or decoders, whatever, only use the blue uplink, so that there's no risk of oversubscription of any sort, and I have a very robust architecture. I'm going to do a second cut on the switch, calling it the green VLAN, the port number 11, 12, up to 20. Let's call it 20. And I'm going to use a second green uplink, okay? These ports on the left are going to be categorized as access mode port. It means that the encoders and decoders have nothing to do with VLANs. They are not even aware, but this traffic incoming into the switch will be placed in that blue VLAN. The uplinks on the other side will be simple VLAN trunks, but only the right color traffic will go through. And also we make sure that the native VLAN information is set to the same VLAN so that the central switch doesn't know anything either. So that the traffic remains untagged end-to-end for the blue devices up to the core switch. So this method does not require any configuration on the central switch. The central switch is absolutely not aware that you have physical VLANs on your access switches. So if I have a few other network engineers in the room right now, you may tell me, hey, wait a minute, what about multicast and IGMP? Because of course, as soon as we have several VLANs for multicast and IGMP, it brings up some complexity. That is true, okay? In that case, we are not going to have any complexity because we took care of IGMP. At NETGEAR, we call that IGMP Plus, and this is totally automated, so the IGMP multicast does not require any configuration. So let's see how we are going to configure that on the first switch. You might be afraid, but it's very simple at the end. We are going to enter into the configuration mode of the first switch, create the VLAN 10, 20, 30, and 40, the blue, green, red, and yellow VLANs. We are going to enable IGMP Plus so that everything gets automated so that we don't have to worry about IGMP for the VLAN 10, 20, 30, and 40. And then we are going to disable the spanning tree. Very important, right? Because if you have several individual links from one switch to the other, spanning tree may shut them down. So disabling spanning tree might be the best way to go at this point. Then we are going to configure the first group, the blue ports, ports number 1 to 10, put them into the access VLAN mode for the VLAN 10. Same thing for the other 10s and 10s and 10s for the VLAN 10, 30, and 40. And then we just need to configure the trunks ports. Each time start with the first one, the blue one, and this is going to be a trunk mode. Only the VLAN 10 will be allowed, and of course the egress traffic to the core switch will be untagged because we specify the native VLAN 10 as well. And we are going to do that on the 3 other uplinks, and we are done with the configuration of the first switch. So now we have configured the first switch up there. Again, the central switch does not require any specific configuration because for him there's no VLAN. And of course, we will just replicate that configuration, maybe save the configuration of the first switch and upload that configuration to the 6 other switches or 7 other switches to make sure that you have the very same everywhere. So this is another method for controlling the multicast flows across a network. So let's review the benefits and maybe some drawbacks. Stacking is probably a very, very elegant method. Stacking is a good method because you remove complexity from the multi-switch with only one big switch. But multicast across the stacking links, unless you have ample bandwidth connectivity, might be sometimes a challenge. Link aggregation is a great, elegant method as well. It used to be very complex for IGMP in between switches. We fixed that. But the traffic in between the link aggregation groups sometimes also might require additional configuration. Like, for instance, specifying the multicast IP addresses of each transmitter in order to alleviate, or I would say ease, the algorithm for the parsing between the legs in the link aggregation groups. The third method might seem a little bit more complex, but frankly, this method gives you the most control, okay? Because you can then segregate ports, you can partition the switches and make sure you control which port is using which uplink. And this is probably a good robust method for large-scale information. Thank you for your attention. That was a real pleasure. Laurent from the ISE on the SDVoE booth.